Okay, so yesterday we were talking about these generalized gamma matrices. There were 16 matrices that we indicated as this manner. The what we call scalar one, then the vector one, that are the gamma mu, then the tensor one, mu nu, this sigma mu nu, the sigma mu nu that you know was built out of the gamma mu. Then there is a pseudo-scalar one that is gamma 5, and is defined I, gamma 0, gamma 1, gamma 2, gamma 3. And then there was the axial vector part, that is gamma 5, gamma mu. And we said that these are 16 matrices. For them, we said that there are the following property. And we check already some of them. Okay, the first property A is that gamma, any of these gamma square give plus or minus the identity matrices, and we proved that for few of them. We checked them with few of them. And B, that given a gamma n different than the identity, there is at least a gamma m such that gamma n, gamma m is equal minus gamma m, gamma n. This was the second property. Okay. The third, and out of these we got also that trace, out of these two, trace of gamma n is equal 0, except when n is the scalar. Okay, and D, the last one, it was that gamma A is always possible to prove that given two gamma, gamma A and gamma B, their product is always equal to a number FABC, gamma C. Okay, a number, this is not summed, this is just a number, and gamma C is one of these 16 gamma. And the last property is that gamma n are linearly independent. Okay, we check this. We check for some of them. We check these, I think. We check the trace, right? Okay, and now let's check the last two. For example, okay, so let's check these. Okay. For example, let's take, okay, let's take for gamma A, so we are checking these now. Gamma A, let's take gamma mu, and for gamma B, let's take gamma nu. Then we have to prove that the product of two can always be written as the combination with some coefficient of a gamma C. Well, gamma A, gamma B is equal gamma mu, gamma nu. That is equal gamma mu, gamma nu minus gamma, and let's take mu different from nu. Gamma mu, gamma nu over 2, because these two, nu, sorry. because these two anti-commutes, as they are different from mu and nu are different, there is no G mu nu, okay? But this one can also be, or well, actually, well, let's put in this way. This one is also equal minus E sigma mu nu, okay, without having, so this is equal sigma mu nu, so is one of the, sigma mu nu is one of the things, so we have gamma A, gamma B, and the coefficient this time is minus I, this is the coefficient F A, B, C, and then sigma mu nu, that it was the gamma tensor, so gamma tensor. So we proved, we checked, at least for one, is easy to check for all of them. Now the last thing is the linear independence. So linear independence, it means that if I sum, if I do a linear combination of them and equal 0, that these are linear independent means that this is true only if all an are 0. Okay. Now, so let's see if this equation tells me that all the coefficients are 0, then this is equivalent to saying that they are linear independent. It's the usual definition of linear independence. So let's multiply on the right by gamma m with a gamma n different than is, than the identity, okay, and then we have sum an gamma n gamma m, okay, and this now, okay, and of this quantity now let's take the trace. So we will have, for example, the case when the two are equal, so we will have an trace, am trace gamma m square. So the first case is when n is equal m. Let's remember that here I sum over all n, and then I have plus trace in, but now I know that these two, because of the condition D, will be equal to f n m L gamma L with some gamma L, okay? These are numbers, I can pull them out. So here I have now equal am, the trace of these we know is, this object is I plus minus I, the square, so basically the trace is 4 plus, is plus minus 4, the trace of this, because they are 4-dimensional things, plus this, but these are numbers I can pull out. I have the trace of this that is 0. So I have that the trace is equal to 4 am, okay? But I started from a quantity that was 0, I multiplied by this, so I have started with the quantity before taking the trace and before multiplying from a quantity that was 0. Okay, so this quantity is 0. That means I do this quantity is 0, and this tells you that the coefficients are 0. Okay. Now, another important quantity that, I mean, why these matrices are important? These matrices are important because basically sandwiching this quantity with the Dirac wave function, we will get what are called bilinear spinors, and these are what are most of the observable of the theory. So let's start this small chapter that is called bilinear spinors. Okay. Now, so bilinear spinors are psi daga x, gamma, one of these gamma, gamma n, psi of x. Okay, so these are called bilinear spinors. Now they are called spinors because these objects, these Dirac quantity are spinor. They are bilinear because there are two of them. So they are linear in this and linear in this. And here I can put any matrix 4 by 4. These are all matrix 4 by 4. These 16 matrices are all 4 by 4. And so I sandwich with a 4 component here and a 4 component here. Because let's remember that these psi are not just one wave function, but they are 4. Okay, another thing is here we look at this quantity gamma 5, and one of the property is easy to see, that gamma 5, gamma mu plus gamma mu, gamma 5 is equal 0. And this is very simple to prove, so they anti-commute, while the gamma 5 with sigma mu nu commutes. Okay, and the reason is very simple. Let's do it. This object is proportional to gamma 5, gamma mu, gamma nu, minus gamma nu, gamma mu. Okay. Well, we can prove this first one. We will prove also the first one, but now let's prove this. Well, what happens is every time gamma mu, gamma 5 goes through a gamma mu, okay, it picks up a minus sign. So basically it goes through 2 times and it picks up a plus sign. The same with this one. That means when you put on the right or on the left, you get the same quantity, so they commute. Is it clear, that one, without me doing the calculation? So as I go across this, I get a minus because of these things. Then I get another minus, and I end up with the gamma 5 on the right of this expression. The same here, and they have not changed sign. So gamma 5 on the left or on the right, it gives me the same result, then it means the commutator is 0. Let's prove this one instead, that gamma 5 and gamma mu commutes. Gamma 5 is I, gamma 0, gamma 1, gamma 2, gamma 3, and gamma mu. I have to prove that this quantity plus gamma mu, gamma 0, gamma 1, gamma 2, gamma 3 is equal 0. Now, how I do that? Well, this quantity will, we can, you see, every time it passes through these 4, it always gets a minus, except when it meets something that is the same. For example, suppose gamma mu is gamma 2, then here it does not pick up a minus sign, but what I can do, I can continue with the gamma 2 that is on the left, okay, without exchanging the 2. So I know it does not pick up a minus sign. So how many minus signs it pick up? 1 from here, nothing from here, 1 from here, 1 from here. So 3 minus, and I have brought to the right, and the total is a minus. Here there is a plus, so the sum is 0. Is it clear? Even if okay, I repeat it, okay? Slowly. Take this and start commuting with this object. Every time, if the index are different, it picks up a minus sign. So let's suppose that gamma mu is gamma 2, that mu is 2. Then it picks up a minus sign from here. Then when I arrive here, I know that the 2, the square would give 1, but I don't do that. I start moving the gamma 2 that is on the left. I don't exchange the 2. I move the gamma 2 that is on the left, so it picks up a minus sign with here, and then it picks up another minus sign with here. So altogether I have 3 minus signs. If I have 3 minus signs, the total is a minus. And it always happens, whatever is mu. If mu were 1, the same trick I would do with the gamma 1 there, okay? So basically, when it gets to the one that is the same, instead of exchanging that you would get nothing, you start moving the gamma 2 that is on the left, okay? And in that manner you get 0. So these are important relation. Now, another thing is that we will study is how this quantity will transform. Let's remember that how the spinor transform. The spinor transform in this manner, where SA is nothing else than exponential minus I4 sigma mu nu omega mu nu. This is a set of parameters, but I can simplify, and let's suppose it's just one parameter, like for example, like we did for the boost or the rotation along tree. So there is only one parameter, sigma mu nu, but then there is a matrix. This is just one parameter, but this was a matrix. So there is a matrix that I indicate In that carries the two indices mu and nu. So this is a simplified notation. Okay. Now, because of this, of the form of this, we immediately have that SA and gamma 5 commutes. Why? Because of this. Gamma 5 and sigma mu nu commutes. Here there is only sigma mu nu as a matrix, okay, that care about the other 4x4 matrix. So we have this quantity. If you remember, among the transformation, these are the generic Lorentz transformation, we had the space reflection that we studied yesterday. The space reflection was A phi gamma 0. Now we can ask, as these commute with the Lorentz, what happened with the P? Well, with the P it anti-commutes, because this is made of gamma 0 and gamma 0 and gamma 5 anti-commutes. So this is the commutator with the minus, this is the anti-commutator. So the gamma 5 with P commute. Okay, now we are equipped with all the things. So basically, let's write down here SA gamma 5 commutes and P, the space reflection with gamma 5 anti-commutes. Now we are equipped with everything to find out how the bilinear spinors that will be actually our observables. The observable of the theory will always be something like that, you know. The most simple is psi daga psi if gamma n is the identity. Now we can see how they change under a Lorentz transformation, okay. Now let's start with the simple one, for example with the identity. So we have psi prime x prime psi prime of x prime. This is nothing else than psi daga prime x prime gamma 0 psi prime x prime. So I have started with the simplest bilinear, the one where the matrix gamma is the scalar or the identity. Now this one is psi daga s x s daga gamma 0 because this quantity is this. Then I have gamma 0, then I have s psi of x. Okay. Now we proved that, I think yesterday or the day before, no, even before, we proved the following, that s daga gamma 0 is equal gamma 0 s to the minus 1. Eventually we will reprove, if you don't remember this, that when the s daga goes across the gamma 0, it becomes the inverse. Or if you want, well, okay, yesterday we proved that, how did we prove? Yeah, it was yesterday we proved that S dag is equal gamma 0 s to the minus 1 gamma 0, right? Remember that we said, look, the S are not all unitary. The one related to the rotation are unitary, but the one related to the Lorentz are not. But they all satisfy this quantity, this relation. Well, this relation is nothing else than this, because if you multiply on the right this expression by gamma 0, you get gamma 0 gives you the identity, then you have S dag gamma 0, so you get this expression. Okay, so this expression we already knew. Okay, clear these things? Then let's use this expression there, and we have that this is psi dag. S dag gamma 0 is gamma 0 s to the minus 1 s psi of x. So this one is the identity, and we get psi dag gamma 0 psi, so psi bar x psi of x. So note that this quantity is a Lorentz invariant quantity because it's the same as this one. And this is an important result, that psi bar, this is Lorentz invariant. If you do psi dag psi, this is not Lorentz invariant. You know, what is the difference between this and this? There is a gamma 0. And you see this gamma 0 plays a crucial role, because this gamma 0 with the S dag allowed us to use the relation that brought on the other side S to the minus 1 and cancel the 2. So this is not Lorentz invariant. While this one, psi bar, that is psi dag gamma 0 psi, is Lorentz invariant. So this explains why most of the quantity you will see in relativistic quantum mechanics, they have always the psi bar. Okay, the reason is exactly that the presence of these make this bilinear a Lorentz invariant quantity. This one is not. This is a very important point, okay, that I can ask in the final exam. Why this is not a Lorentz invariant, for example. One simple question is, why this is not a Lorentz invariant? And so you have to do the Lorentz transformation and see that it's not. And you know, the crucial ingredient was this gamma 0 there, because that gamma 0 combined with the S dag allowed us to write S to the minus 1 because of that identity. That means it allowed us to bring on the other side S to the minus 1 and cancel with the S. If there weren't this cancellation, you would not get rid of the S, so you would not have Lorentz invariance, because somewhere some piece of S that signal the Lorentz transformation would remain. Okay, so this is a very important result. Okay. Now let's see another object. That's another bilinear. Is the one that with the gamma 5. So this we can say is Lorentz invariant or is a scalar. Also another equivalent manner is that this is a scalar. It does not change under Lorentz transformation. Okay. Let's now see build another bilinear, that is another one that we will often find, and is the following: psi bar gamma 5 psi. Okay, and let's see under a generic Lorentz transformation how it works. We will see that this transforms as a scalar also under Lorentz transformation, but it has a strange property under space reflection. Okay, space reflection is here, exponential I phi gamma 0. Okay, so let's look at this quantity. The transform one is psi daga gamma 5 psi. And this I have psi prime daga gamma 0 gamma 5. Okay, psi prime. This is equal psi daga S daga gamma 0 gamma 5 as psi. Now let's remember that okay, let's remember first these things. I have psi daga gamma 0 s to the minus 1, and let's remember that gamma 5 and s commute. So here I have used the relation that I had before, and here I use the fact that gamma 5 and s commute. So what I get, that these two cancel. I have psi daga gamma 0 gamma 5 psi, and this is psi gamma 5 psi. So this also seems to be a scalar under Lorentz transformation. But now let's see what happens when instead of doing a proper Lorentz transformation, I do a space inversion. If we do a space, let's do a space inversion. Okay, so this is a scalar under proper Lorentz transformation. Let's do now a transformation of this quantity under a space inversion. So space inversion. So we have psi prime gamma 5 psi, that is psi prime daga gamma 0 gamma 5 psi prime. But the transformation, let's suppose, is just a transformation due to the space inversion. Now, P and gamma 0 commute because P is proportional to gamma 0. Okay? And the P with gamma 5 anti-commute. Okay? So, what we can do is the following. We can we bring this on the other side, but as it anti-commutes, we bring a minus, so minus psi daga P daga gamma 0 P gamma 5 psi. Then P and gamma 0 commute, so this is equal pi daga pi gamma 0 gamma 5 psi, because P and gamma 0 commute. So this minus sign was because these two anti-commutes. Okay, now pi daga, let's see what is pi daga, is E minus I phi gamma 0 daga, that is gamma 0. Then I have I, this is this object. Then I have I phi gamma 0, that is this object. Then I have gamma 0 gamma 5 psi. Now this and this cancel, this and this give me 1, and I have minus psi daga gamma 0 gamma 5 psi. But this is equal to minus psi gamma 5 psi. So under a space reflection, it changed sign. It changed sign under space reflection. So the scalars who behave in this strange manner, that under a Lorentz, a proper Lorentz, they transform a scalar, but they change sign under time refraction, are called pseudoscalar. Are these transformations clear? Okay. Now, let's take another one, but we will not do all of them, but we will do many of them. For example, let's take a bilinear spinor when gamma is gamma mu. So let's take this. And let's see how we change under Lorentz transformation. So we take psi x gamma mu psi x, we transform, so let's transform and let's see how things change. So this is psi prime x daga gamma 0 gamma mu psi prime x. This is equal psi daga s daga gamma 0 gamma mu s psi of x. Now we have to remember one of the defining relation for S of A. If you remember, S of A satisfies the following relation. S of A gamma mu S to the minus 1 of A is equal to A mu nu gamma nu. Let's remember this was one of the relation that S satisfied, and it was that relation that we needed to have invariance of the, or covariance of the Dirac equation. And from this we found the solution of S. You remember this was already 3 or 4 lectures ago. And we also have the other relation that is gamma 0 S daga gamma 0 equal S to the minus 1. That is the one that we used before. In a different form, we brought the gamma 0 on the other side. That means this is S0 gamma 0 equal gamma 0 S to the minus 1. Okay, so now let's start doing things around. So here we do psi daga S, and this we do gamma 0 S to the minus 1. Then we get gamma mu S psi of x. Now we have this object here, S to the minus 1 gamma mu S. Is the same as this one. You can say, oh, but the S is to the other side, but this is any S. So it could even be S to the minus 1, because S to the minus 1, being a group, it belongs to the set of S. This is any S. So it could also be the inverse, the S to the minus 1. So this quantity, I know that I can put equal, this quantity I can put equal A mu nu gamma mu, this quantity, because of this relation. Even if S to the minus 1 is to the left, it doesn't matter, because this holds for any S. So I could take any S related to A, so I could take even the S of the minus 1. Okay, and I get this quantity. Sorry, yeah, this quantity. Then I have psi of x daga gamma 0. But now these are numbers, I can bring them out. These and these give me, so I have A mu nu. This object is nothing else than psi daga S. Here I have gamma nu psi of x. So you see, this quantity transform according to this coefficient, but this coefficient is like the x transform, so it means this quantity is a vector. They transform like the x transform, so this bilinear complicated object made of two spinors and of gamma mu, they transform as vector transform. Now let's see what happened, this transform as vector under proper Lorentz transformation. Let's see under space inversion what happened. Okay, can I cancel here? Okay, let's start from here. Let's see how they transform under space inversion. So space inversion. Well, I will have psi daga x, p daga, gamma 0, gamma mu, p, psi of x. Well, these and these are nothing else than gamma 0 with a phase here and the opposite phase there. So the two phases cancel and we get gamma 0, gamma mu, gamma 0, psi of x. This gives me the identity. So I have psi daga x, gamma mu, gamma 0, psi of x. And now let's see here. Now, if mu were a space index, then so with mu a space index, then these would change sign and I would end up in minus psi daga gamma 0 gamma I psi, that is minus psi bar gamma I psi. So under space reflection, they change sign the space part like exactly a vector. A vector x change sign under a space reflection. Let's see the case instead mu equal 0. With mu equal 0, so mu equals 0, then we would get gamma 0, but I can immediately take this gamma 0 and get the psi. So I would get psi daga gamma 0 psi, but this is minus psi bar gamma 0 psi plus. I have done, if I put here mu equals 0, I don't have to do any, I take this and sandwich with this in order to produce the psi bar. I don't have to do. So the time part does not change under space reflection. It means this is a vector. It's really a vector. It transforms as a vector also under space reflection. Change, like x, it changes sign the spatial part and it does not the time part. Of course, no, they are vector under Lorentz transformation. Under Lorentz transformation, you see, they transform with this coefficient in front. So under Lorentz transformation, proper Lorentz transformation, they are vector. They transform as vectors. Under, instead, the space inversion, the space part change sign, the time part does not change. So they are not invariant. Well, they are invariant under these. You can say the time part is a scalar under space inversion if you want, but it doesn't matter. Now, if instead of this quantity you take, we will not keep going with these things because it becomes too long, but this was a vector in every sense. Instead, if you take the following object, psi bar x gamma mu, gamma 5, psi of x, it's easy to see that these, under a proper Lorentz transformation, transform as a vector, because there is this index mu, and it transforms as a vector. But if you do a space reflection, then there are troubles. Under a space reflection, the space part does not change a sign at all. So, and let's work out at home, not as an homework, but work out at home what happened under a space reflection for the time part of this. Okay? Some of the problem that I tell you, look, do it at home. It might end up that then it's part of the final exam, so you better do, even if I don't say that it's an homework. So that means if I take mu equal I, it does not change under space reflection. For mu equals 0, well, you have to find out. But anyhow, this part is enough to qualify that as a pseudo vector, not a real vector. It transforms under Lorentz. It transforms as a vector under proper Lorentz as a vector. So it, in every effect, in every respect, it is a vector. But then when you do the space reflection, it has strange property. Different than x, it does not change sign. So we say it's a pseudo vector. And you check at home what happens when mu with the time part of this. So this pseudo vector is time part. What happens when I do a space reflection? Okay? Okay. Now, well, you have seen that the Dirac equation, if you go back and read carefully these things, the Dirac equation was characterized by the alpha and beta matrices or by the gamma matrices, according to which one you use. Okay. And they had some algebra among them. You know that the alpha I had to anti-commute. The beta square was 1, and so on and so forth. Now, that one that we chose were not the only representation of the alpha and beta or the gamma matrices, not that gamma, the small gamma. There were other representations. For example, there is a representation in which we can choose that all these, let's call the new matrices gamma mu. It's possible to choose these matrices so that every element is imaginary, the real part of all this. So we can change the alpha and the beta that had that particular form, and that seems is the only solution. Is not the only solution of that set. I mean, they have to satisfy those constraints, if you remember, and they had to satisfy those constraints because we wanted that the solution of the Dirac equation satisfy the mass share relation, at least in operatorial form, and that induced some commutation between the alpha and the beta and the associated gamma. The gamma, you remember, are built out of the alpha and the beta. But are they the only solution? No, they are not the only solution. You can choose other solution instead of the gamma mu that are related to the beta. Other gamma said that the real part is 0, and then the usual things is satisfied. But now look at the equation, at the Dirac equation. At the Dirac equation, if you use this strange gamma mu, is this, and this, there is an I here. This is purely imaginary. The real part of this is this. So this is real. At least this operator is real. So this is also called real version of the Dirac equation, but is also called this gamma and this equation the Majorana representation. Okay, so when you hear about the Majorana representation, it means, well, it means many things, but basically it means Majorana was able to choose the gamma matrices, not the 16 gamma that I told you before, the gamma that are, I mean, the analog of this, okay? So he was able, but let's indicate in another manner. In that manner, the Dirac equation was real. So he was able to build gamma matrices that had only imaginary part. The real part was 0, and as a consequence of this I, the Dirac equation was real. So these are called Majorana representation. How they are built? Well, let's remember the old one. The gamma 0 was I, 0, 0 minus I, and the gamma I was 0 sigma I minus sigma I 0. The sigma I Pauli matrices, just to remind you, are these. Now, these are the usual Dirac matrices, gamma matrices. The Majorana one, I build them in this manner. Gamma 0 equal gamma 0, gamma 2. So this is the definition of the gamma 0 of Majorana. And you get 0, sigma 2, 0. The gamma 1 is I, gamma 0, gamma, and you see that this is purely imaginary. The sigma 2 is this, is purely imaginary. Okay, let's take the gamma 1. The gamma 1 is defined in this manner and is I, 0, sigma 1, 0. Also is pure imaginary because sigma 1 has that form, but there is an I in form. The gamma 2 is I, gamma 0, so is I, the identity 0, 0 minus I. And the gamma 3, never remember if I think is the gamma 3 is I, gamma 0, gamma 3 is I, 0, sigma 3, 0. Okay, and it's easy to see that they are all imaginary. It's also easy to see that they anti-commute among themselves, like this. Let's just do one example. So let's take, for example, 0 and 1. Then let's check this for 0 and 1. That means G 0, 1. This is equal to 2G 0, 1, and this equals 0. And now let's start from something that we know give 0, that is gamma 2, gamma 1 plus gamma 1, gamma 2. We know that these give me 0, even if they have nothing to do with this. Okay, this we know it gives 0, so this matrix is 0, but also this is 0 because of the commutation relation that we know between the gamma matrices. Okay, now we can multiply this by gamma 0 square and get gamma 0 square, gamma 2, gamma 1 plus gamma 0 square, gamma 1, gamma 2. Okay, then what I can do is I can bring one of these gamma into here, one of these two gamma 0 I bring into there, then I change sign, I have gamma 0, gamma 2, gamma 0, gamma 1, and I do the same there, plus gamma 0, gamma 1, gamma 0, gamma 2. So what I've done, I have brought one of the gamma 0 in between, I change sign so I get this. But now, these one are the Majorana things, so this one is gamma 0, and this one is gamma 1 plus gamma 1, gamma 0. So it satisfies the right relation. And we can continue in this manner. On the book you will find some of them. Okay. Now, okay. Any questions so far? So the Majorana representation is very important because somehow having gamma that are purely imaginary, the Dirac equation is real. Some call the Majorana representation not just the gamma matrices, but the manner the spinors are represented. Okay, and but let's stick to the book. Otherwise, as the book used this notation, let's stick to the book. Now we will do two cases of Dirac equation that are so now we start jumping for the last part of this course. We will just do small part of various chapters. So this is the, I cannot find the page, but it's the Dirac equation in the rest frame and this solution. So the small part we will do now is, let's look at the Dirac equation in its rest frame, when the particle is in its rest frame, so that the P, the space part of P is 0. So if you go to the index, you will find rest frame. Let's see. Yeah, okay, is 271. Okay. This is the first part that I don't think we did. Of section 2.3, page 120. So it's the first what we will work out is 271 and 272, and then we will put it equal. So page 120 and page 157, the first page only. So the things we do, even if I take, you know, basically here that it takes 2 pages, and you will see it will take me 20 minutes. So I know that I go fast, but in 20 minutes I only do 2 pages of the book. So basically this chapter is called, not chapter, but okay, so rest frame, it means P equals 0. Okay, P, the vector P. But if we use the correspondence principle, it means the operator is 0. But that an operator is 0 implies that when you apply on psi, any function is 0. Okay? So basically, this, what does it mean, this? This means IH ddx I on psi is 0. Okay, so let's start with the Dirac equation, IH d psi dt equal minus IHC alpha I ddxi sum over I psi plus m0 c square beta. These are the alpha and beta matrices psi. Now, we are in the rest frame, so as we are in the rest frame, these things is 0. So the equation boils down to be d psi dt equal m0 c square beta psi. Okay, so this is the Dirac equation in the rest frame. Now, do we know the form of the beta? Yes, we know. I don't want to go back again, and the form was this, I 0, 0 minus I. So that equation, this equation with this form, writing all the components, is IH d dt. Now let's write the four components, psi1, psi2, psi3, psi4 is equal m0 c squared, then beta, and beta is 1, 1, minus 1, minus 1, psi1, psi2, psi3, psi4. Now, this equation is very easy to solve. Why? Because they are not coupled one with the other. The derivative of psi1 is equal to mc squared psi1. So from here, you derive four equations that are IH d dt psi1 is equal m0 c squared psi1. EH d dt psi2 is equal mc squared psi2. IH d dt psi3 is equal minus m0 c squared psi3, and IH d dt psi4 is equal minus mc squared psi4. You see, so they are not coupled. What couples them was the alpha and made the solution difficult, but we worked out, remember the free Dirac particle, we worked out the solution also with alpha different from 0, that means not in the rest frame. Now, these one, the solution of these are very simple. Psi1, the solution of this is 1, 0, 0, 0, exponential minus I m0 c squared over h times t. The solution of this one, psi2, is 0, 1, 0, 0, exponential minus I m0 c squared h times t. The solution of this, psi3, is 0, 0, 1, 0, exponential. Now it changed sign because I have a minus, so I have plus I m0 c squared h t, and psi4 is equal 0, 0, 0, 1, exponential I m0 c squared h times t. So you see 2 with the minus and 2 with the plus. Now there is an even more compact manner to write all these. Okay, so you see, if I ask you as an exercise, solve the Dirac equation in the rest frame, it's nothing fancy, but it's just that things. Now, there is a more compact manner to write all these. People have introduced a notation that is the one that you find on page 157, and is the following. They, instead of writing, they write psi r. R is for 0, 1, 2, 3, 4, sorry. And then they say is an omega r 0 exponential minus I epsilon r m0 c squared over h times t, where r, this r is not a 2, is a r, is 1, 2, 3, 4, and epsilon r is 1 for r equal 1 or 2, and is minus 1 for r equal 3 and 4. Because you see, this epsilon r, if it is plus 1 for these two, and is minus 1 for the other two. And then I have these objects, and these objects are what they call the basic spinors, and is basically the following: omega 1, 0, because it's at time 0, this is giving the evolution, and this is at time 0. Omega 1 is 1, 0, 0, 0. omega 2 is 0, 1, 0, 0, omega 3 is 0, 0, 1, 0, omega 4, 0, 0, 0, 1. These are called basic spinors, and they have well, easy to remember. At least this is a compact form. You don't have to write all four, just put this index. But remember that this means the only element different from 0 in this spinor is the first. The only element different from 0 in this second spinor is the second. The only element different from 0 here is the third, and so forth. Okay. Now, this solution has also a nice things. It is, if you remember, we had generalized the concept of helicity. That was sigma, and sigma is a vector that is a 4x4 matrix, with the sigma matrix is defined in this manner. Now, if you take sigma 3, that is sigma 3, 0, 0, sigma 3, then it's easy to see that these are eigenstate of this sigma 3. And in particular, it's easy to prove that if you take sigma 3 psi r, so psi r is this solution, you get plus or minus psi r, with the plus for r equal 1, 3, and minus for r equal to 4. Okay? So these, it's always interesting to find out of which observable they are eigenstates. These objects are eigenstates also of this generalized spin, because this is the spin for up and the spin for down. And you see the plus is for 1 and 3. And in fact, if you put that, sigma 3, this is nothing else than 0, 0, 0 minus 1, then 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0 minus 1. And then you see that there is a plus for 1 and 3, and there is a minus for 2 and 4. Okay? Now, so this is the equation and the solution for a massless particle. That means the part that contains alpha is being dropped out. Now let's do the other case, the case in which the mass is not there, so massless fermion. Then beta, the part with beta is not there anymore, okay? But before doing that, is it clear? Can I cancel? No, this is for the rest frame. Now we will go and do for massless spinor, for massless direct fermion. This is not massless. You see, it has a mass here. So this is the solution for what is above there. Direct equation in the rest frame and this solution. This is a very simple exercise, but it's always important. We don't do. This is a course that is reduced in number of hours, 20 hours only, so I cannot do everything, but at least the most basic things you should go out of this course and have it. Okay, let me cancel it. So now we will do, and I hope to finish today so that tomorrow I can do something else. Okay. So the Dirac equation for massless particle Well, a typical massless particle with a spin 1/2 is the neutrino. The neutrino now they say it has a mass, and because of this mass it has oscillation among various species of neutrinos, but up to a few years ago it was considered massless, and the mass actually that they found is very small. So one example is the neutrino, that is a massless particle. By the way, this part that we will do is on page 333, and we will not do everything. There is a huge amount of material, so just take notes of what we will do, because we will only do few things, okay? Now, first of all, let's go and do the classical, not the quantum, the classical massless particle. Now, one thing that you should know is that a classical massless particle, its velocity is c. That means like a photon. The only particle that they know has no mass is the photon, okay? And its velocity is c. How you get that is c, the velocity? Well, let's take the mass-energy relation. If the mass is 0, you get E squared minus P squared C squared equals 0, if the mass is 0. Now we will prove this, but it's a trivial thing that most probably you know or you have read by yourself, but we did not do in special relativity because we did a very quick review of special relativity. So from here you get that E is equal plus minus PC. Okay, this is the mass-energy relation for a massless particle. But now let's remember the general form of E. E was mc squared square root 1 minus v squared c squared, and P was mv 1 minus v squared c squared. Then you see that if you take the limit of m going to 0, there is a problem. It seems the energy would go to 0. But, well, we have the photon that has an energy different from 0, so the energy is not 0, and this momentum also is not 0. You know, radiation make some momentum, and it can move things. So it means that I cannot do this naive limit. And in fact, if I send m to 0, but at the same time I send v to c, I get 0 over 0, and that limit can be different from 0. Or otherwise, I must better is to insert that relation here. Then I have, if I insert this relation here, I get mc squared 1 minus v squared c squared equal mv 1 minus v squared c squared. But I have to multiply by c. So I have c, I have plus minus, and I have the modulus of that. So basically I have inserted that two relations here, inside here. Then the mass, you see, cancel, and these two relations are equal only if v is equal c, right? So from the mass shell relation I get this relation between energy and momentum. Then the general expression of the energy is this, the energy expression of the momentum is this. If I equate them, I get that the velocity is equal to the velocity. So massless particles travel at the velocity of light. So when a few months ago somebody said that the neutrinos were going faster than light, you know, they even have a mass, so they can go faster than light. At most, if they had no mass, they would go at the velocity of light, but, you know, everything can happen in the nature always surprises us. That is the good point. And actually, theoreticians had already built a model in which some models in which neutrino goes faster than light. They are like tachyons. Everything that goes faster than light is called tachyons, and it violates a lot of things like causality. If you go faster than light, basically, you can be born before your father. Okay, so that means you have to be careful because causality is really very important things. And when you go faster than light, one of the things that you might violate, then people preserve causality and violate something else, unitarity and so on. But I mean, I would not laugh at this error that there was in this experiment, you know, because, well, of course, it was something that was not plugged in correctly. Maybe they should have checked more carefully. But that means if some other experiment come up saying that neutrinos goes faster than light, I would not immediately point my finger and say something must be wrong, because nature surprise us and will continue to surprise us. So it's a pity that it was a mistake and that okay, so now this is the classical part. Let's look at the quantum part. N is 0, so the Dirac equation is just this form. EH d psi dt equals C alpha P psi of x. There is no beta. Why? Because beta is multiplied by m. M is 0, and so there is no beta. Okay? And we know the alpha from the Dirac equation have to satisfy this relation, alpha I, alpha j, plus alpha j, alpha I equal delta 2ij. We knew that the alpha to satisfy this relation, not because of this equation, but because in general of the Dirac equation. Now we don't have the beta, so the other two relations that have to satisfy commutation between alpha, anti-commutation between alpha and beta, and the fact that beta and alpha square has to be 1, then that one I don't put. I have only this relation. Now, if you look at this relation, imagine Dirac at the beginning done for massless particle. So he would have got this. Then this, the realization of this algebra can be done by 2 by 2 matrices. That means this, if we had to satisfy only this, then the alpha I we could choose to be Pauli matrices, 2 by 2. So the massless Dirac equation can be realized not by a 4 by 4, but by a 2 by 2, because this relation can be satisfied by the alpha equal sigma. Now, this is one thing, but now I will show to you that even if you start with 4, you can always reduce to 2, to an equation that has only 2 components. So let's start with the, so basically then this one, then the psi now is not psi 1, psi 2, psi 3, psi 4. It's not like this, but it's a 2-component thing. So let's call phi, and it has a phi 1 and a phi 2. Okay, and the equation then becomes, that equation then becomes IH d phi dt equals C sigma dot P on phi. And so you see the massless, the equation, the Dirac equation for the massless particle actually is equivalent to a 2, not to a 4 by 4 equation, but to a 2 by 2 equation. Now there is another manner to, if you don't like this approach and say, okay, well, this is a realization, but I want to stick with my old alpha matrices, then I will show to you the same. So let's remember, let's stay with 4, okay? Let's remember alpha I, alpha j, plus alpha j, alpha I, where 2 delta I, j, I, and then alpha I beta plus beta alpha I is equal 0, alpha I square is equal beta square is equal I. And we have seen one realization of these matrices, that is the following. Alpha I equals 0, sigma I 0, beta equal I 0, 0 minus I. But you remember before I said, well, of the gamma matrices or of the alpha of the beta, there is not only one realization, there is another one, like the Majorana one. Well, there are many, many more. Let's call this realization, it is the one that we use up to now, the Dirac one. Well, there is not only this realization, there is also another realization called the Weil realization. That means that satisfy those relations, because these algebraic relations are the only important things, not the realization. This is a particular realization that satisfies this, but there can be different realizations that satisfy this. In fact, Weil, who was a mathematician in, a mathematical physician, realized that there was another realization. It is the following: sigma I 0, 0 minus sigma I, and the beta of Weil equals 0 minus the identity 0. Okay? If you take this, it satisfies all that. Okay? So this is the Dirac realization. Of that algebra, and this is the Weil realization. But then let's look at if we use the Weil realization. First of all, let's check it, because maybe you don't believe it. Let's check that at least it satisfies this relation. Okay, so let's check that the Weil satisfies this relation. So alpha I, alpha j plus alpha j, alpha I, this is equal sigma I 0, 0 minus sigma I, sigma j 0, 0 minus sigma j, minus sigma j 0, 0 minus sigma j, sigma I 0, 0 sigma I. And if you do, you get sigma I sigma j plus sigma j sigma I 0, 0 sigma I sigma j plus sigma j sigma I. And this is nothing else than 2 delta ij, and this is 2 delta ij. And so this is nothing else than 2 delta ij I. So the Weil realization of the alpha satisfies this relation, and it's easy to see that it satisfies also the other, okay? Well, as the alpha are different, I am allowed to also write the wave function in a different form. So let's write the wave function in a different form. So let's cancel this. We had already from here the things that it could be realized as 2 by 2, but we stick to the 4 by 4, but in the Weil realization. Then let me write the 4 by 4 as 2 by 2, phi plus and phi minus, where each of them, phi plus and minus, are 2 row vectors. Okay, so this is a 2 vector, this is another 2 vector. Altogether is a 4 vector. Okay. Then let's write again the Dirac equation, but let's use the Weil matrix, the realization of Weil of the alpha matrices. If you do that, you immediately get the following things. I have put a mass. But if you, I have put a mass, and now let's insert these, and let's use the sigma matrices in the Weil realization, this one. The equation you get is IH d phi plus, remember phi plus is this, over dt is equal minus IH sigma phi plus minus m0 c square phi minus. And the other equation is IH you see, so the four-dimensional Dirac equation become this, each of them is a two-dimensional Dirac equation because the phi plus and phi minus, and they are coupled because phi plus pulls in not only phi plus but also phi minus. But what they are coupled? By the mass. If the mass is 0, then this term is not there, and then I get two uncoupled equations, right? So you see that effectively, using that representation, the massless particle is represented by two equations that are actually identical, modulo this sign. Okay? So OI modulo this sign, it means one is the same as the other if t goes into minus t. So basically, with one equation is enough, either this or this. Okay? So in the Weyl representation, when you have no mass, the equation becomes equivalent to a two-dimensional equation. Okay, you see, what couples the upper component and the lower component is the mass term, but the mass is not there, and then you are left with these things. So let's choose one of the two. Let's choose the phi plus. And let's go on and see what happened. I will not be able to finish today, but okay. So these two equations, now let me cancel also this. The mass term is not there. So you see this is a two-dimensional equation. This is a two-dimensional equation. And they are not coupled anymore. Phi plus evolve according only to phi plus. I only give instruction to the initial condition of phi plus to have everything, and phi minus. So they are not coupled anymore. It was the mass that coupled the phi plus and the phi minus. Now they are not coupled anymore. So let's choose phi plus, and one is equivalent to the other. The difference is this sign, but I get this sign if I send t into minus t. So phi plus goes into phi minus if is the same as phi minus. The solution I get for phi plus of t is the same as the solution I get for phi minus with minus t. So again, for massless particle, I just need two equations. This was Weyl who realized that, but then various people did not believe that, and somehow, okay, now let's take this equation. Let's write down not with the derivative, but with the pi. So with the momentum, we have d phi plus dt equals c sigma dot p phi plus x. And let's now, what we want to do, we want to solve this equation. So let's choose a solution of this form. Phi plus, this is an ansatz. Some normalization factor in the book is specified, and there is, you will see, a square root of e and so on and so forth. I don't want to enter why there is square root of e and so on, because it will become really long. So there is a normalization factor. Then I put exponential minus I px over h bar u plus of p. So this I did for fixed p. So I choose a fixed value of p, and I choose a solution of that form. Now, this P and X is four-dimensional, P times X means P0 X0 minus P times X. So this is a four-dimensional scalar product. Okay. Then if you write in this manner, when you do the derivative with respect to t, you will bring down a C P0. Okay. Remember that if you want to do the derivative with respect to t, this object is CT. Okay. So remember, then if you insert this solution into this, what you get is P0 U plus equal sigma dot P U plus. So this is an equation for the U plus, this unknown quantity that I don't know. Well, this equation is interesting because, for example, if you apply the helicity operator to both sides, remember the helicity operator was sigma dot P over modulus of P. It was the helicity operator. Let's apply on both sides, okay, on this side and on this side. On this side, okay, I have this object, and on the other side I have sigma dot P and here sigma dot P. Then use the famous formula that tells you sigma times a vector times sigma dot another vector B is equal to A times B plus I sigma times A wedge B. Okay, well, if you do that, so apply this, on this second one, use this relation, this is 0, you get only P squared, but P only in the things. Then you have a P0, pull it out, and you have sigma dot P, but sigma dot P, so I apply sigma dot P here, I have sigma dot P times P0. P0 is a number, it comes out, and I have sigma dot P applied on this. But I know that sigma dot P is equal to P0, so I get again P0. I had already another P0, I get P0 squared. So if you apply the helicity operator, the result you get is this, P0 squared minus P squared U plus equals 0. That means that P0 is equal to plus minus P. That is the usual relation for massless particle, okay? This is just a check on that things. So let's go back to our equation. This is just a check that the energy, the mass-energy relation is the one of a massless particle, because you know, you see, if they give me an equation like that, it's true that there is no mass, so I should expect that it's mass 0 and that the mass-energy relation is the one of a massless particle. But I wanted to check, and I got it in this manner. Now let's go and let's stick to this and let's try to solve that equation. Now let's suppose that is fixed P and is along Z. Then if it is along Z, this equation becomes the following. P0 U plus equal sigma 3 modulus P U plus. But this one, we know from the relation before that it was equal to modulus of P. U plus equal sigma 3 modulus of P U plus. So it means sigma 3 U plus equal U plus. You agree? This was the, if we move along the direction 3, then I have sigma 3 times P for this part, sigma 3 dot P. Okay, I get this. But then I use the mass shell relation and I know that this is plus minus, if you want, plus minus thing. So now I can cancel this and I get plus minus things. So this U plus is the plus minus solution. Okay? Am I doing right? Yeah, well, if I choose plus, then the solution of this is 1, 0. Okay. Now, if I choose plus, it means here I have chosen plus. It means positive energy. So this is positive energy solution. And let's see this solution if it has some helicity. Let's take the helicity operator. Let's apply on U plus, and what you get is easy to see that, you know, basically this is sigma z, P and P cancel, U plus, and this is, with this solution, is plus. So positive helicity, and positive helicity it means right-handed. Positive helicity, it means the helicity operator has eigenvalue plus 1, but is also called right-handed things. Now, we will analyze these tomorrow, because, you know, there are massless particles like the neutrino, but they are not right-handed, they are left-handed, in the sense that their spin, right-handed, it means the following. This is P, this is the spin. The spin and P, these are pointing in the same direction. You see, look the helicity. The helicity tells me the projection of sigma on P, and the projection of sigma on P divided by P, this is the helicity, okay? The projection of sigma on P. Now it tells me that that solution is plus 1, so it is S, and is equal to plus 1, S is in the same direction as P, right? So this is the right-handed and the left-handed is when S is opposite to P, and here the helicity operator sigma dot P on P, this has eigenvalue plus 1, this has eigenvalue minus 1. This is called left-handed. Of course, there might be particles that their spin does not point in the direction of P. Okay? But for massless particle, the spin always points in the direction of P or in the other direction. Why? Because this is the equation of motion of a massless particle, and when you apply the, you see that when you apply the helicity operator, you get eigenvalue plus 1 or minus 1. So that is another result. Massless particles not only move at velocity c, but their helicity can only be plus 1 or minus 1. Okay? So that means they can only be in this direction or in this form or that form. Now tomorrow we will continue from this.